So welcome again. In this video, we will be dealing with some basics about rotation metrics, translation, then the details of support structure we are using in additive manufacturing process. What is the importance of support structure, and about the minimization of cost and the support structure. So these are the main objectives of this session. So when we are manipulating the STL files, we have to use these types of techniques such as rotation and translation. So when we are orienting a particular object, for example, when I am rotating a particular STL file, that means I'm rotating that particular file. So we should know the basics behind the rotation, and we should know the basics behind the rotation metrics. In mathematics, a rotation is a transformation that turns a figure around a fixed point called the center of rotation. The resulting image is a rotated version of the original figure. To describe such rotations, rotation matrices are employed. These matrices provide a mathematical representation of the rotation, defining how to transform coordinates from the original figure to the rotated one. Rotation matrices are widely used in various fields, including geometry, physics, and computer graphics. In geometry, they are used to describe the orientation of objects in space. In physics, they are employed to describe the rotation of objects, such as the rotation of the Earth around its axis. In computer graphics, they are used to rotate objects in 3D space, as shown in the figure, creating animations and simulations. The use of rotation matrices simplifies many computations involving rotations, such as calculating the angle and axis of rotation, converting between different coordinate systems, and combining multiple rotations. They also allow for efficient and accurate transformations of objects in space, making them a valuable tool in many applications. Then coming to the rotation metrics. So this is rotation metrics about X, Y, and Z axis. A rotation matrix is a mathematical tool used to describe the rotation of a three-dimensional object around an axis. It is a 3x3 matrix that can move a body as a rigid unit without deforming or altering its internal geometry. The matrix is designed to perform a variety of operations such as rotating, scaling, and translating the object. When a vector, which represents a point in the object, is multiplied by the rotation matrix, it changes the direction of the vector without affecting its magnitude. This means that the length of the vector remains the same, but its position in the object has changed. The rotation matrix is widely used in computer graphics, robotics, and physics to describe the orientation and position of objects in three-dimensional space. Then coming to the translation. A translation process is a mathematical operation that involves moving every point in a given space by a fixed distance in a specified direction. Like Pxy is moving from this point to Px dash y dash. Similarly, this triangle, this polygon is moving from this position to this position, or this triangle is translated from this C to C dash. This movement is described as a rigid motion because it does not change the shape or size of the space, only its location. There are different ways to interpret a translation. One way is to see it as the addition of a constant. Yeah, one way is to see it as the addition of a constant vector to every point in the space. Another way is to view it as a shifting of the origin of the coordinate system. In other words, a translation can be thought of as a way to move the entire space by the same amount in a particular direction. Translations are commonly used in geometry, physics, and computer graphics to describe motion, displacement, and transformations of objects and images. They are an essential concept in mathematics and have many practical applications in various fields of science and engineering. Then coming to the support structure. What is a support structure used in 3D printing technology? A support structure is a crucial component of 3D printing that is added to a model during the slicing process. When a model is sliced, the software analyzes the design and identifies any overhanging or bridge structures that require additional support. The support structure is then generated and added to the model. The support structure is an additional part that is printed alongside the model and is designed to provide temporary support to the overhanging or bridge structures during the printing process. Without this support, the overhanging or bridge structures would not be able to maintain their shape and could collapse during the printing process. Once the printing process is complete, the support structure needs to be removed. This is called a post-processing operation from the model. This is usually done by manually away the support structure or dissolving it in a solvent. The FDM printer is one of the most commonly used 3D printers. It operates by melting and layering the filament material one layer at a time. The printer head moves along the X, Y, and Z axis to create the object layer by layer. During the printing process, the support structure is printed alongside the model and is removed once the printing process is complete. Then we are going to deal with the optimal orientation. Optimal orientation of the structure is very important because see, I can orient this is see let us take this is my part, so I can orient this part in different orientation. So which orientation is best so that my cost is minimum, at the same time the support structure usage is also minimum, because we are using support structure means it's completely wastage. So we have to restrict the use of support structure to minimum, and if when we are considering the cost, we have to reduce the cost also. So the optimal orientation of the part is very relevant in the case of additive manufacturing process. So think about your orientation process. Is it a worst orientation, or is it a best orientation, dealing with cost and quality? Because cost and quality are the two important factors. Quality is very high, at the same time cost is, we have to reduce the cost and we have to increase the quality. So by reducing the cost and increasing the quality, we should choose the proper orientation of our part structure. When deciding on the optimal orientation for the 3D printed part, several factors need to be taken into account. One of the most important is surface finish. Depending on the orientation of the part, the surface finish may be smoother or rougher, which can impact the final appearance and functionality of the part. Another critical factor is build time. The orientation of the part can affect how quickly it's printed, which can impact the overall production time for the project. Support structure is another consideration. Certain orientations may require more support structures to be added, which can increase the complexity of the print and may require additional post-processing work to remove the support material. Shrinkage and curling are also important factors to consider. Depending on the orientation of the part, shrinkage or curling may occur during the printing process, which can distort the final dimensions of the part and make it unusable. Finally, part cost is a significant consideration. Depending on the orientation of the part, the amount of material used may vary, which can impact the overall cost of the project. Given all of these factors, it is impossible to optimize all of them at once. Hence, determining the right orientation for a part is a matter of compromise and balancing the different factors to achieve the best possible outcome. Then, coming to the minimization of the cost. Cost minimization is an important financial strategy that involves reducing cost and expenses while maintaining the quality of goods and services provided to the customers. The main goal of cost minimization is to achieve the most cost effective way of delivering goods and services to the required level of quality. This process involves analyzing and reducing expenses across all areas of the organization, including production, marketing, administration, and sales. However, it is important to note that cost minimization is not about reducing quality or shortchanging customers. The focus is on maximizing efficiency by identifying areas where cost can be reduced without affecting customer satisfaction. In other words, the aim is to maintain a balance between cost and quality while ensuring that the needs and expectations of the customers are met. To achieve cost minimization, companies often employ various cost-cutting measures such as reducing overhead cost, streamlining process, optimizing resource utilization, and negotiating better deals with suppliers. However, these measures should be implemented carefully to ensure that they do not compromise the quality of products and services or cause harm to the company's reputation. In conclusion, cost minimization is an important strategy that businesses can use to improve their profitability and competitiveness. By reducing expenses without compromising quality, companies can achieve greater efficiency and profitability while ensuring that customer needs and expectations are met. When we are dealing with the additive manufacturing process, what is the total cost? So total cost means pre-processing cost, then the utilization of the machine, that is again another cost. Then we are using two types of materials. One is main material and support material. So what about the material cost of this main material and yeah, again the total cost involved in the additive manufacturing process are the pre-processing cost, the machine utilization cost, material cost, and finally post-processing cost. So these four costs added together, you will get the total cost involved in an additive manufacturing process. Then what is called a pre-processing cost? Pre-processing means before starting the machine operation, what are the costs involved? That is what is called a pre-processing cost. One is we have to deal with the time related to model position, support generation, model slicing, toolpath generation time. So all these times you have to add together and you have to multiply with the staff cost per hour and plus the computing facility cost per hour. Once again, model position time, add 4 time such as model position time, support generation time, model slicing time, and toolpath generation time. And then we have to multiply this time with the staff cost per hour and computing facility cost hour. Again, you have to add this with the setup cost multiplied with the staff cost per hour plus machine utilization rate. So machine utilization rate we can calculate with the help of an equation, that is m plus c by t divided by 365 divided by 15. So m is the maintenance, annual maintenance, that is the 15% of initial machine cost, and t is the machine life. So with the help of this equation, we can calculate the pre-processing cost. Then next is the building cost. Building cost, we can calculate the building cost with the help of equation such as build time multiplied with machine utilization rate. Machine utilization rate we can calculate with the help of equation m plus c by t divided by 365 divided by 15, where m is the annual maintenance, that is the 15% of the initial machine cost, and t is the machine life. Then material cost. As I already mentioned, there are two types of materials we are using. One is main material and the support material. So we have to add these two costs. The main material cost plus the support material cost will give you the material cost. Then what about the post-processing? Post-processing means once you finished your printing process, you have to remove the support structures, you have to do some finishing operations, etc., etc. So the post-processing involves post-processing cost multiplied with staff cost per hour plus the miscellaneous cost. Miscellaneous cost such as say, for example, we are doing some UV oven for the stereolithographic process, or hot isostatic processing for metal, then waterworks for FDM process, etc. So what are the miscellaneous cost? So miscellaneous cost added with pre-processing cost multiplied with the staff cost per hour. This will give you the post-processing cost. So our aim is to minimize the cost. So once again, the total cost involved in an additive manufacturing process is the pre-processing cost plus building cost plus material cost plus post-processing cost. Our aim is to minimize the cost. Okay, this technique is called a cost minimization model. Then another model is called a support minimization model. What is support minimization? Again, we have to, as I already mentioned, we are using support structures for supporting our part. The support structure is not connected with the part. So that means we will remove the support structure during the post-processing operation. That means it's completely waste. So we have to restrict the use of support structure to a minimum. So the support minimization model is dealing with that. Additive manufacturing is a process of creating three-dimensional objects by adding successive layers of material. During the printing process, some areas of the object may overhang or face deformation due to thermal stress. To maintain the structural integrity of the object, support structures are necessary. These are the support structures. This black color represents the part, our final 3D printed part, and this color represents the support structure we are provided. These structures help uphold the overhanging areas and prevent deformation during the printing process. The design of this support structure is critical as it affects not only the printing quality but also material consumption and post-processing time. Poorly designed support structures can lead to defects such as surface roughness, warping, and sagging, which can negatively impact the final product's functionality and aesthetic appeal. Moreover, inefficient support structures can waste material and increase post-processing time, leading to higher cost and longer production times. Therefore, it is essential to consider the design of support structures carefully. Factors such as orientation of the object, the type of material used, and the printing technology employed can all influence the design of the support structures. By optimizing the design of support structures, additive manufacturing can produce high quality, functional, and aesthetically pleasing objects with minimal material waste and post-processing time. So I'm concluding my video. In this video, we were introduced to a wide range of options available for rotation and translation in the field of computer graphics. We provided with a detailed explanation of support structures and their purpose in the manufacturing process, additive manufacturing process. We also learned that support structures are crucial in additive manufacturing process as they provide a stable base for the object being printed. We also explained how support structures function by helping to prevent the object from collapsing or distorting during the printing process. Moreover, we also learned about the significance of orientation in the manufacturing process, especially in additive manufacturing. The orientation of the object during the printing process can significantly affect its strength, quality, and overall performance, overall appearance. We also explained that choosing the right orientation is crucial to achieving the desired result in additive manufacturing. Finally, we explored different models used to optimize the additive manufacturing process, such as cost minimization and support minimization. We also explained that these models can help to reduce the production time and cost while achieving the desired result. By minimizing the amount of support material used and optimizing the printing process, we can achieve high quality prints while minimizing waste and reducing cost. So next video, we will deal with the slicing process. Thank you.